Right. Good morning. Thank you for joining me. So this talk is about software architecture and specifically diagramming and describing and explaining software architecture. For those of you who don't know me, my name's Simon Brown. I'm an independent consultant specializing in software architecture. Show of hands, who here uses UML? Yeah, that's more than I was expecting, but it's still not everybody. So when I ask this question in my travels around the world, it's typically a little bit lower than this. And maybe this is a sign of why companies get me in. So typically it's about 10% of people who use UML. And there are lots of reasons for this. And I think I've heard every single reason you can possibly imagine as to why people don't want to use UML anymore. And there's a book about this you can go and buy. It's called 97 Ways to Sidestep UML by No Formality. And I've literally heard all of these different excuses. Some of these are just crazy. You know, you'll be seen as old-fashioned if you use UML. It's not expected in Agile. The value is in the conversation. And, you know, since we've been doing the Agile thing, we've perpetuated lots of these myths and lots of these excuses for not using UML. And, of course, one of the recommendations for drawing architecture diagrams to explain your software to other people is to just use a whiteboard. And although that kind of makes sense on the face of it, we don't teach people how to do this. So one of the things I do is I get to travel the world and I run software architecture diagramming katas exercises where we give people requirements and I say, go draw some pictures. And we get diagrams like this. And that. And this one, which is my favorite, I think. That's like London Heathrow Airport. This one here shows that our system does business logic. The logical view. The stormtroopers. Lots of crossing out, renaming. These are real pictures from real workshops I've run over the years. And to be fair, some of these are the more extreme diagrams because I'm trying to make a point. Let me show you some diagrams from a workshop I did last month. It's not as bad as some of the diagrams I've just shown. Part of the exercise is we switch diagrams, so every group gets a different set of diagrams to look at, and we ask them to give these diagrams a score out of 10. What score would you give this diagram out of 10? 8, 7, 6. This scored a 7. It's not great, it doesn't tell you anything. What about this one? What score would you give that? 4, 8, no, 7. This one? 7. That one? 7. That doesn't tell you anything. This one here? 7. I'm not making this up. All of these people scored other groups 7 out of 10. This one here? 7. This one here? No, 6. And the funny thing about this diagram is it actually has more detail than the others. And for some reason, the teams thought, no, this is too much and we don't understand it, so we're going to rate it lower. So this whole just use a whiteboard thing doesn't necessarily work very well. Now, the exercises I run, they tend to be quite short. They're like 60 to 90 minutes. So maybe if people had more time or they had a tool, they were allowed to use computers, they could draw better diagrams. And unfortunately, that's not the case. So if you go to Google and you do a search for software architecture diagram, it goes, sure, here are some diagrams for you. And these are all garbage as well. So they look nice. They're all, you know, nice squarish boxes and stuff, and we've got nice colors. They all have exactly the same problems as the hand-drawn pictures. We have boxes and no lines. We have different shapes, but we don't know why. Different colors, we don't know why. Different sizes of boxes. We have layers, both horizontally and vertically. We have acronyms, no titles. There's just a whole bunch of stuff going wrong with all of these diagrams. The building industry. If we look at the building industry, if you ask an architect to draw you a floor plan of where you live, you'll get a floor plan. And you can look at the floor plan and go, yes, I have windows, doors, I get this. If we were asked to draw a floor plan, we go, yeah, sure, here you go. Here's a floor plan of my house. Like, what? But logically and conceptually speaking, this makes perfect sense. So these little red dots here, that's my Wi-Fi hotspot. Because it's important. But don't ask me what the dashed lines mean, I have no idea. So I think we need to take a little bit of a kind of back to basics approach, because we should be engineers. And we're trying to be artists. And I think we should do something a bit more engineering. And the whole point of this, of course, is if we want to be lean and agile and we want to move fast as a team unit, we need to communicate well. And I've visited lots of organizations recently where their lack of communication is literally slowing them down, because teams don't have a common vision of either what they are going to build or what they are building or what they have built. One of the other things against UML potentially is that it's very technical in nature. And if you want to describe your software systems to developers and architects, that's fine. If you want to talk to product owners, scrum masters, testers, whatever, there's a whole audience out there that doesn't necessarily know UML. So we need to target, again, as storytelling, we need to target our stories at different types of audiences. So my top tip in all of this is when you're drawing architecture diagrams, don't think like an architect. Think like a developer. And this sounds very counterintuitive, but when I'm running these design exercises, the developers and the people who attend my workshops, they can do the design part. So they can design a solution, but when you ask them to draw it, they forget everything they've ever known, they put their architect hat on, and they start drawing all these really high-level, fluffy, conceptual pictures that literally make no sense. And one of my goals here is when I'm asking people to draw architecture diagrams, good architecture diagrams, I want them to reflect reality. So when you show them to another developer, they go, yes, that's exactly what we're building. I think in order to do this, we could look at UML. UML gives you a standard set of things and a standard notation to diagram those things. I think the things, the abstractions, is actually much more important than the notation. And one of the reasons people cite for not using UML is that the notation is very complicated. So I'm an abstractions first kind of person here. Notation second. And although this might sound a bit foolish, if we go get two local maps of this area, the two local maps are going to show the same things, aren't they? The towns, the train lines, the bus routes, the schools, the churches, the museums, the points of interest. The two maps will show the same things, the same abstractions, but they'll likely use different color coding, line styles, notations, shading, icons, symbols, and so on. And the key to understanding a map is the key. There's a key or a legend on the map, and it tells you, when you see this sign, that's what it means. And I think that's a really, really powerful and simple concept that we can just borrow. So what are the abstractions? When I'm thinking about describing and documenting and explaining a software system, for me, that software system is made up of one or more containers, not Docker. So I've been teaching this approach for well over 10 years now, and Docker got popular and kind of stole the word container. By container, I basically mean an application or a data store. So something that runs your code, something you need to deploy and run somewhere, or something where your data is being stored. So in real terms, a container might be a mobile app running on your mobile device, a back-end server-side app, a console app, a Windows service written in C#, a Python script, a database schema, a folder on a file share, an Amazon S3 bucket, a DynamoDB, all of that type of stuff. That's what I mean by container. We look inside these containers. I'm going to say they are made up of components. So components is a hugely overloaded word, but basically what I mean by components is a grouping of stuff, modularity, nice boundary, nice, clean, simple interface, running inside a container. So that's the important part here. We've got a hierarchy. And if we look inside components, they're mostly made up of code-level elements. So if you're building your Java apps, you have a bunch of components built with Java classes and interfaces, for example. And that's it. It's a simple hierarchy, a hierarchy of structural elements that we can then use to describe software architecture. And then that leads me to the C4 model, which is in the title of this talk. So if you want to point other people at the C4 model, you can go to c4model.com. C4 stands for context, containers, components, and code. And it's 4 levels of diagram that map onto those levels of abstraction. as Tendai said in the keynote, I'm going to tell you a story, and that story is going to be linear. The one thing I do not want you to take away is Simon says we must draw diagrams in this order, because a lot of people do that, and then they kind of superimpose Simon therefore says we should do design in this order as well, and that's not what I'm saying. So this is just a collection of diagrams you can draw in any order to describe your software systems at different levels of detail. That's basically what this is all about. And it's essentially, the way to think about this is diagrams as maps. So I live in Jersey in the Channel Islands, and if you open up your Maps app on your smartphone and you do a search for Jersey, you'll get that picture by default. So Google Maps, for example, zooms straight in and says, oh, you're interested in Jersey, this is what Jersey looks like. If you want to know what the major places are in Jersey where I live, that's useful. If you've never heard of it and you don't know where Jersey is, it's pointless. You have no context. So you get to zoom out or zoom in to tell different stories, to get different levels of information. And it's the same thing with these diagrams. We have different levels of diagrams to tell different stories to different audiences. And the purpose of this talk is really just to show you the C4 kind of core diagrams, the static structural diagrams. But once you have a good idea of your static structure, and you're able to talk about your static structure, you can then use these same concepts to draw runtime diagrams, sequence diagrams, deployment diagrams, and so on and so forth. So this is kind of a really nice starting place. I'm going to show you a bunch of example diagrams based upon an internet banking system. So imagine we work for a bank, and the bank wants us to build an internet banking system. So I'm going to start from the top, again, storytelling, and I'm going to draw a level 1 system context diagram. And a system context diagram basically shows the thing you are working on or building and stuff around it in terms of other systems it talks to and the people who use your system. So we're going to start with a box in the middle. And this represents our internet banking system as a software system. Don't worry about notation and shapes and color coding. I'll cover all of those tips later. So in order to draw this diagram, we now need to ask a bunch of questions, like who's using it? So now we look at roles or users or personas, and we come up with a bunch of people who are going to be using our software system. So in this example, let's say there's only one type of user. It's personal users, personal banking customers. So you and I, as account holders, we want to use the internet banking system to get information about our accounts and maybe make some payments. Where does this system get its information from? Well, let's say the bank has an existing software system, a mainframe back-end banking system, and that's where all of the core banking data is stored. So we're going to have some interaction with that. Let's also imagine, for the purposes of this story, that we need to send emails to our customers. And rather than creating our own email system, we're just going to use the bank's internal email system. So that's a really nice, simple example of a system context diagram. It basically shows you that's the thing we are working on, and this is the environment, the context around it, in terms of people and other software systems. For larger environments, you have more boxes, and there's a longer question there about how do you deal with larger diagrams, and we can cover that in a Q&A if you want to. So that's level 1. It's nice and high level, nice and straightforward. Not much tech choices on here. It's great for a really wide range of audiences. So as developers and architects, we now want more detail. So what's inside that internet banking system? What tech is it made of? How does it work? So now what we're going to do is we're going to pinch to zoom in to that internet banking system box, and we're going to drop down to level 2. And level 2 is a container diagram. And this is showing you all of your apps and data stores and how they relate and run at runtime. And we're going to build this up piece by piece. So the currently empty-looking box here, that is the internet banking system box from the previous diagram. That's the thing we're going to look into. And we're still going to show the people and the external systems we have some dependency on. Caveat time, what you're about to see is how I might design an internet banking system. You might not agree with my design. That's fine. Park those thoughts. But this is how I might design the diagram. And of course, I needed to do that in order to show you a diagram. So first of all, we're going to have a deployable web application. So imagine you open up your web browser, you go to mybank.com/internet banking, you get a bunch of static content back in your browser. HTML, CSS, JavaScript. That's going to be served from this backend web app, which I'm going to say is a Java Spring MVC app. Once you get all of this static content back into your browser, I'm going to say that actually that's going to be a single-page app, essentially running client-side in your browser. So I'm going to model that as a separate box on this diagram. So now I've got a bunch of JavaScript code essentially running in my web browser. That's my UI for my internet banking system. It's a single-page app. In this case, it's JavaScript and Angular. How about we give people a mobile app as well? So let's build a separate mobile application using, in this case, the cross-platform Xamarin framework, and that's an alternative UI that we can present to our customers. How do the single-page app and the mobile app get data from the back-end banking system? Well, they need to go through something. So I'm going to say we're going to have a separate API application exposing a bunch of JSON over HTTPS endpoints. That's a separately deployable Java Spring MVC web application. So now we have two web applications where we're deploying server-side. You could have one, I'm choosing two. We need to sign in. So we go to the front page, we need to add username, password. Imagine we work for the bank, we go ask the bank, can we put our usernames and passwords in your back-end banking system? They say no. So we need somewhere to store our own data, so let's have our own database schema to do that. So that's basically, in this case, an example container diagram. It's showing you the various applications and data stores, the technologies they're built with, a bit about responsibilities on there, and how they connect at runtime. So each of these containers is mostly, and I'll tell you later why I'm using the word mostly a separately deployable thing. And the links, the lines between the containers are mostly inter-process communication calls, so something with a network involved somewhere, typically. So that's level 2. Let's imagine that we are now in a team and we are working on the API application. And we want to see how that code base is structured. So now we're going to pinch to zoom in, and we're going to drop down to level 3. And I'm now going to draw you a components diagram for that API application. And we're going to do the same thing. So this currently empty box here represents the API application box from the previous diagram. It's used by the single-page app and the mobile app, and we're going to add some other stuff to this picture. So you open up the mobile app. You need to sign in. So I'm going to say we need some sort of sign-in API. So we're going to have a sign-in controller. That's going to use some sort of security component, which is going to do authentication against our credentials in the database, hopefully using hash passwords and all the rest of it. Once you're signed in, you get a list of your accounts. Let's imagine that that's serviced by a separate accounts summary controller. Again, that's providing another API endpoint. And that's going to use this really horribly named mainframe banking system facade component, which talks to the horrible back-end banking system. If someone wants to reset the password, yeah, we'll give them the way to do that as well. In a more real-world example, you could see you'd have many, many more components on this diagram. And again, there's another question here about how do you deal with larger systems. But this is a nice, simple example of the components that sit inside that API application. It's at this point, of course, that we now need to start talking about lower-level tech choices. So we've got Spring Beans and Spring MVC REST controllers, and there's some other high-level tech choices and frameworks on here. If I were to open the code base for this API application, I would expect to see very clearly these 6 things somewhere in my code base. So at level 3, at the component level, your architecture diagram now needs to start reflecting your code structure at a high level. So there needs to be a nice one-to-one mapping between concepts on this diagram and concepts in your code base. Whether those concepts are language-level modules, Maven modules, Gradle modules, components, packages, namespaces, jar files, DLLs. So there has to be some organization structure which is reflected on your diagram. So that's level 3. Level 4, so I don't recommend doing level 4. I'm going to say that again, because people always miss this. I do not recommend doing level 4, because it's not worth it. And often you can just generate level 4 automatically from your IDEs. To tell the story, I'm going to show you an example. So let's imagine we are working on this horribly named mainframe banking system facade component thing, and we want to see inside it class diagram. So this is where UML is super useful for documenting and diagramming those lower-level aspects. If you want to diagram level 4 for complicated components or when there's something a bit funky going on, feel free. But in 99% of situations, do not draw level 4 diagrams. Just automate them for your IDs. So that's the diagrams. System context, containers, components, code, and we're done. Notation's important. And there's lots of subtleties in the notation and the example diagrams that I wanted to go through very, very quickly. So some tips for notation. Tip number 1, put titles on pictures. And I know this sounds super obvious, but when I run my workshops, 80% of diagrams first time rounds do not have a title. And you have no idea what you're looking at. So when I'm titling a diagram, I want to be very explicit about 2 things. What type of diagram is this, and what's the scope? So if I'm drawing a system context diagram for a financial risk system, I'll literally label it like that. So I'm very specific and very clear here. Layout, if you don't have access to whiteboard, if you're writing on paper, it's kind of hard to raise. You can use sticky notes and index cards representing your boxes, move them around, get a layout you like. That's fine. I wouldn't necessarily deliver diagrams as a collection of sticky notes because they will fall off and it just kind of looks a bit cluttered. I will try to aim for some visual consistency. So if I've got multiple levels of detail, I will try to always keep my people in the same visual location on the diagram canvas, for example, and I'll try to use the same color codings and shapes across all of my levels of diagram. And you would have seen that in the examples I've just showed you. Be super careful with acronyms. If you are targeting your diagrams at technical people, like developers and architects, don't worry about explaining MVC and ASP and JDBC and all that stuff because we probably get that. Focus more on the domain-specific acronyms, the business acronyms, or the funny jargon that lives in your companies. So code names for systems or code names for teams, that sort of stuff catches out new joiners really, really quickly. Boxes and lines. So let's start with boxes or more specifically elements. When I'm drawing a diagram for the first time, I'm going to forget about shape and color. And I'll talk about why in a second, but I'm going to just draw plain, boring boxes. And inside my boring boxes is a bunch of text. If you look at the top 3 levels of the C4 diagrams, so context, containers, components, these are basically the only 4 types of elements I expect to see on the diagrams. So it's a very simple language you can teach people. So the system context diagram shows people and software systems. The container diagram shows people, software systems, and containers. And the component diagram potentially shows all of these things. So every box is going to have a name. And naming is hard and whatever, but hopefully we're going to give everything a nice, simple, easy-to-remember name. I'm also going to be very explicit about the type of the elements. So I'm going to write in the box, this is a person or this is a software system, because then we know what we're getting and there's no guessing. For the 2 technical things down here, the containers and the components, this is where we can start to weave in those text choices. So this is a database schema or this is a Spring MVC app. The rest of the text in the box is a short description, either as a sentence like you see here, or maybe just 5 or 7 bullet points to list out the key responsibilities of that element. And it's at this point people say, well, why are you putting so much text in your boxes? Because that's not how we do architecture diagrams. Well, that's why they're a problem. So here are 2 example architecture diagrams. This is the one on the left is what we typically do. It's just a bunch of named boxes. And I do something like that on the right. If you saw this diagram on the left for the very first time, and I said to you, can you describe what the content updated does? Your response would be, it updates content. Yes. What about the file system? What does the file system do? It stores files. So the names are not particularly helpful, but over on the right-hand side here, we've got more text. So even if the names are a bit odd and a bit ambiguous and a bit vague, at least we can now read the text and go, okay, the name doesn't make sense, but now I know what the thing does. So we're adding a degree of explicitness to our diagrams. But do keep that short. I've seen people writing entire essays in the boxes, and that's not what we're striving for here either. Lines. Pay some attention to lines because lines give you structure. Lines glue your boxes, your elements together. My preference here is unidirectional lines only. So all of my arrows go one way. So you'll never see my diagrams with straight lines with no arrowheads or lines with arrowheads on both sides. And this raises an interesting question. Which way do you point the arrows? And it's up to you. So there are no hard and fast rules in any of this. My preference is for thing A calls thing B, or thing A depends on thing B. If you want to show events or messages or information flow, that's absolutely fine. Just make sure the direction of your arrow matches the text you put on the arrow to describe it. The other kind of catch here is that most relationships are actually bidirectional, aren't they? So if we think back to the internet banking system, we've got the single-page app, and that's making a request to the API app, and the API app is sending a response back, essentially. So it's a bidirectional relationship. And although that makes sense, if we show both directions for every relationship, we're going to get a very, very cluttered diagram really, really quickly. So what I'm going to do instead is I'm going to summarize the intent of those two arrows in a single arrow. So I would rather say something like that. The single-page application makes API calls using the API application. I will try to avoid uses. Again, uses is quite a general, vague, generic term, so I'll try to be as specific as I can, but keep it short. And having said all of this, sometimes you do want to show both directions. So if you've got a bidirectional relationship, but those two directions are very different in nature, very different in intent, then I will show those directions. So maybe we have two microservices, A and B, and maybe at startup time, A can request a list of stuff from B using a synchronous call. So that's one relationship. And then maybe at runtime, as events are coming in, we've got a kind of broadcast thing going on as well. So because those are two very different types of relationships, I want to show those very clearly on the diagram. Another trap people fall into is they kind of hide the true story. So imagine you're drawing a container diagram, you've got a microservices architecture, everything's going into and out of a message bus. You tend to get hub and spoke diagrams that look a lot like this. And again, although that's factually correct, we've got a couple of microservices here stuffing things into a bus and stuff coming out, we may be missing some really important information. So what I'd rather do is perhaps draw something like this instead. So miss off the message bus and instead say, actually, there's a point-to-point relationship here between A and B, and we're just using Kafka or Rabbit as the messaging mechanism for doing that. So again, there are no hard and fast rules here. It's really, do the diagrams tell the story that you want to tell? And add more words. A lot of this is adding more words to make stuff much more explicit. And a really good simple tip here is just read your diagrams out aloud. So in this case, the trade data system sends trade data to the financial risk system. And because that makes sense as a sentence, we're good. Have a key or a legend. So every set of diagrams should have a consistent key and legend to describe shapes, colors, line styles, borders, acronyms, and so on, even if it seems obvious to you. So when I run my architecture katas, we kind of draw some diagrams in the morning, and everybody's using different color Sharpie markers. Then we go for lunch, and then they come back and like, why is this line red? I don't know. They drew it 2 hours ago, but they've forgotten. This is an example of a diagram key, a diagram legend. So this is my container diagram up here for the internet banking system. And that's the key or the legend that I would use to describe this diagram. So that dash box is the system. We've got these various blue boxes here for showing containers, and I'm using different shapes to show different types of containers. People are people. Gray boxes are external software systems. In this case, I'm just saying there are relationships, and I'm not being specific about relationships. But you can be. So if you want to show synchronous relationships different from asynchronous relationships, you could do something like solid lines for synchronous relationships and dashed lines for asynchronous. And you'd have that in your key or your legend. If you wanted to use different colors for different protocols, so maybe green lines are secure, like HTTPS, and red lines are insecure, then feel free. do watch out for color blindness, especially red-green color blindness, and also watch out for black and white printers, because that will happen at some point. So with that in mind, my advice is to use shape and color to complement a diagram that already makes sense. So in other words, if you take a diagram and you remove all of its color and you remove all of the shapes, the diagram should still make sense. And the reason it makes sense is because a lot of the text we add to the diagram helps it make sense. Two versions of the same diagram. Which one do you tend to prefer? That one on the right? Yeah. It kind of looks nicer. It's a bit more aesthetically pleasing. Because you can't read the text, I can't read the text from here either, by the way. Because you can't read the text, looking at the diagram on the right, you're able to kind of understand it and comprehend it a bit quicker because you're confirming what you think you're seeing. So we think those things at the top look like people. Oh, yes, they're people when you read the text. These things look like data storage things down here. So, and again, the shapes help. But fundamentally, these diagrams have the same level of information, and that information is captured in the text. All of this advice goes for icons as well. Do you ever see people drawing these diagrams with the Amazon AWS icon set or the Azure icon set? They kind of look pretty, and they're great if you want to show all of the various Amazon services you're using, but they're basically pointless. Because I don't understand what half the icons mean, and I don't know why these things have been chosen anyway. So these diagrams don't tell me enough from a software architecture perspective. So what I'm going to do here is, if you do want to use icons, feel free, but use the icons to, again, add an additional level or layer of information. So here's an alternative version of my internet banking system container diagram. Now we've removed the color, and I'm now using some icons instead. So if you know what the icons mean, you can see there's a couple of Java Spring apps. There's a database schema. We've got Angular and Xamarin. If you have no idea what the icons mean, it doesn't matter because all the information's in the text. And your key or your legend should have examples of what those things mean, of course. And the whole point of this is what I'm trying to do is make the diagrams able to stand on their own. So whenever I see architecture diagrams, you normally have to have a conversation to explain what the diagram means because the diagrams are basically hopeless. And that's fine if you're there, but often what happens is people draw a diagram on a whiteboard, they take a photo, stick it on Confluence, and that's where it lives forevermore. Someone new joins your team, send them to Confluence, they have no idea what the diagram means, they have to go find the person who drew the diagram, oh, guess what, they quit 4 months ago. So what we'll do is we'll spend another 3 hours with a different group of people at the same whiteboard, redrawing the same, well, not the same picture, something that we hope looks like the same sort of picture, and we just repeat, and we're slowing ourselves down. Any narrative you give, any presentation you give, any supplementary documentation you write, again, should tell stories on top of a diagram that already makes sense. So what I'm trying to do is I'm trying to make us spend our time telling more valuable stories rather than why is that box blue and this one's red. Like, let's just get that stuff down. Next time you draw a diagram, there's a notation checklist you can find at c4model.com. It's a single-page PDF, completely free to download. Run through this, answer some yes or no questions, and this will hopefully give you some tips on how you can improve your software architecture documents. I have a couple of slides left, and then we can open the floor for Q&A. A lot of people ask me, what tooling do I recommend? I'm going to give you 2 recommendations. Recommendation 1, I'm going to give you 3 recommendations. Recommendation 1, do not use Visio. And by Visio, I mean Visio, OmniGraffle, Lucidchart, Draw.io, and Glyphy. All of those stuff, please do not use them because they're general-purpose diagramming tools, and they don't know anything about software architecture. So those are the worst categories of tools you can use. They're the most common, but they're the worst categories of tools you can use. So my first recommendation, there's a whole bunch of tooling out there for the C4 model. C4 Plant UML. So if you've come across Plant UML, it's a way to draw UML diagrams, or not, using text. So you write some text, you throw it through a tool, and it does automatic layouting for you. So someone created a set of macros, a set of plugins for Plant UML, and they allow you to draw the C4 diagrams using a kind of C4 model-ish domain-specific language. all complete, compatible with Plant UML. So that's my recommendation number one. Recommendation number two is my own tooling. Sorry. So I've been dissatisfied with a lot of the tooling out there for drawing architecture diagrams, so I've got a whole bunch of tooling that I've built myself. Some of it's free, some of it's open source, some of it's commercial, but there's a whole bunch of tooling out there you can find that helps you draw software architecture diagrams specifically targeted at the C4 model. No matter which tooling you do use, abstractions first, notation second. So if you take this back to your teams and you want to adopt it, make sure everybody understands those 4 levels of abstractions, the 4 key diagram types, tell them not to use level 4, and then just go forward from there. And that's me. Thank you very much.